Jack Jackson. In this video, we're going to give a very quick overview and review of properties of translation. So remember, a horizontal translation is where we just move the points horizontally, not up or down or left or anything, but just left or right. Algebraically, if we replace x by x minus h in the formula of a relation, then we leave the y values alone, and we add a constant h to all the x values in the table in the graph, and it's translated or shifted horizontally by absolute value of h units. It goes to the right if h is positive and to the left if h is negative, but notice I built in the minus into the thing here. So if you actually replace x by x minus 5 like this, the graph's going to go to the right, and if it's x by x minus x plus 6 like this, the graph's going to go to the left. So here are a couple of examples. Let y be x squared. Here's a basic table of some of the points on this. I just put from -4 to 4 on x. Square them, you get these numbers here. So here's some, just made up some x's here. Here are the corresponding squares. And so these points, if I graph them, give us these blue dots here: 0, 0, 1, 1, 2, 4, 3, 9, -1, -1, and so forth. Now, look at this formula here in red. Y equals x minus 5 in parentheses square. You can easily see that we just took the one on the left, the blue one, and replaced x by x minus 5. So notice it was the x that was changed, not the y. So y will be left alone. So the first thing I want to do, I want these tables to be lined up so that we have pre-image point on the left and the corresponding image point on the right. And all I did was just copy the y's and paste them over here, because when an image point and a pre-image point line up, they have the same y. Now what happens to the x? Well, the x, you actually add 5 to the x. Say -3 plus 5 is 2. Notice this will work because when I take the 2 and subtract 5, now I'm back to the -3, then square it, I get 9. That will keep the 9 the same. So this you can kind of see why the formula has to be backwards. So what did we really do? We left the y's alone and added 5 to the x's. Well, if you add 5 to all the x's and you see how these points correspond, you'll see that they're all just shifted directly to the right 5 units. Similarly, if we take y equals x cubed, here's a table for y equals x cubed, part of the points there, and here's part of the graph there for y equals x cubed, this one right here. And if you notice, what we do here is we leave the y's alone. I'm replacing x by x plus 6 in the formula, so what we really do is subtract 6 from x in the table. So for example, -2 minus 6 is -8 right here. And we leave the y alone, so that gives us our corresponding point. And what this does is shift each one of these exactly 6 units to the left. So this is a horizontal translation. Translation is a technical term. You might also call it scoot it, shift it, slide it informally. So you were just sliding these around. Similarly, we have a vertical translation. If we replace y by y minus k in a formula of relation, we leave the x values alone and we add k to all the y values. Again, notice I built in the minus here. Now, if we look at the blue one here, again, this is y equals x squared, same table, same graph as before for the blue one. What I've done here is if you look at it this first way right here, I think you can more clearly see that the right side of the equation, the x squared, was left alone, and on the left side we replaced y by y minus 3. Solving for y, we get y as x squared plus 3. In that version, it's not as clear what was changed, but in the version up at the top, it's more clear. We see that the y was changed, not the x. So this time when I line up the table, I make sure that the x's are the same. So I'm just simply copying these x's over here. But the y's are changed. How are they changed? Well, here we replace y by y minus 3. We really do the opposite, which is add 3 to y. So 3 stay the same here, but 9 plus 3 is 12 for the y. And what is that going to do? That's going to shift everything straight up 3 units. Okay, vertical shift. Okay, And over here, if I have y equals x cubed minus 2, well, if you look, that's an awful lot like y equals x cubed. But this 2 is not inside the cube with the x. So if I add 2 to both sides, I could rewrite this as y plus 2 equals x cubed, and we see that, oh, okay, the x cubed was left alone, the x is left alone, but the y was replaced by y plus 2. So what do we really do? We subtract 2 from the y, so negative 64 minus 2 is negative 66, negative 27 minus 2 is negative 29, and so forth, leaving the x's alone, and we see that we're shifting down 2 units. Now, in general, we can do both of these things at once, and we can translate by some vector hk. So if you want to translate by the vector, say 2, 3, you want to go to the right 2 and up 3. So you replace x by x minus 2 and y by y minus 3. And that's exactly what I did here. I replaced y by y minus 3 and x by x minus 2. You could also solve for y and put it this way. The top version here is probably the best version for seeing how it relates to this. But if you're going to type it in your calculator, of course, you're going to solve for y. So what this is going to do is do both things. It's going to add 2 to x and add 3 to y. So let's take a point here, say negative 2, 4 on this one right here. So we should be adding 2 to x, that makes that at 0, and adding 3 to y, 4 goes up to 7. And if you do this, everything's going to be shifted to the right 2 and up 3. This one down here shifts left 5 and down 2 by taking x and replacing by, and by actually adding negative 5 to x, which is replacing x by x plus 5, and actually subtracting 2 from y, which is replacing y by y plus 2. And you can see that here in the table and the graph. So let's talk about some things about translation specifically. A general translation requires that we identify the vector by which each point is transformed. In other words, how much we're sliding to the left or right and how much we're sliding up or down. A translation maps any pre-image to a congruent image so that all corresponding distances and angles are preserved. So we call this a rigid transformation or an isometry. The figure, a graph, for example, is simply moved around while maintaining the same size, shape, and orientation. So notice that a translation has no fixed point. Every pre-image point is mapped to a different image point. So no point individually stays the same in the pre-image and the image. But you could have translational symmetry. You could slide every point, say, pi units to the right, and we will get a new graph that is the same as the original. Now, for that to happen, this graph has to go on forever, at least in the direction that we're moving. So if we take, for example, the line y equals x, and we translate it by the vector 2, 2, we're just sliding the line along itself, and so you get y minus 2 equals x minus 2, which is the same as y equals x. Now in trigonometry, we studied several functions that have horizontal translational symmetry, and if it has horizontal translational symmetry, we call those periodic functions. Let me flip back here to an example from a previous one. So, previous video, here's an example of a function which if we take this and we translate it by, I think it was 2 pi over 3, we get the same graph again. Even though this point right here is going to be moved to this point, it's not fixed individually. Since it goes on forever left and right with the same repeating pattern, collectively they stay the same. And so that's called translational symmetry. But a horizontal translational symmetry is also called periodicity or periodic function.